field extensions again. Let us recall what we have been doing in this section, or rather what our objective is in this section. Here we want to show this. We take any polynomial f of x over some field f. We want to show that there is an extension of f, some extension of f that will contain a root of this polynomial. Now that result has now come. This is the result. A general polynomial f of x will come afterwards. Okay, this result specifically tells us about existence of such extensions for irreducible polynomials. Let's see the statement. If px is a polynomial in fx of degree n, it should be of positive degree. N is not equal to 0 and is irreducible over f. Then there is an extension e of f, and that too an extension whose degree over f is equal to n, equal to the degree of the polynomial, and which has a root of this p of x. So once we prove this theorem, then this general case will come as a corollary. So let's see the proof. In the proof, in the very beginning, what we are going to do is we are going to consider the principal ideal generated by this polynomial in this polynomial ring fx. So let phi equal to this be the principal ideal of the polynomial ring generated by p of x. Actually, there is no need to write this much. If we simply write only v equal to this, that just means all these things. But we usually write these things at this level because when we read such a line, it reinforces the idea in our mind. Okay, it makes us remember the things more clearly. So now, because fx is a Euclidean ring, this we have already seen when we in ring theory, we saw that over a field, if we consider all the polynomials with their addition and multiplication, we get the ring which is a Euclidean ring. And in a Euclidean ring, any principal ideal generated by a prime element is maximal. Now, in our Euclidean ring, the irreducible polynomials are prime elements. So this ideal is going to be maximal since, let me continue from here, since p of x is irreducible over f and hence is a prime element in this ring, the ideal phi is maximal, and the result that says this is lemma 396. Okay, and this lemma 396 is actually that result itself we have encountered in the theory of Euclidean rings, that principal ideals generated by prime elements are maximal ideals, but rephrased in particular for polynomials. Okay. Hence, the quotient ring, which we are going to denote by E, of fx by the ideal V is a field. Once you have an ideal in a ring, you can form the corresponding quotient ring, and this is going to be a field because the ideal by which you are forming the quotient is a maximal ideal, and this is one of our ring theory results. And the specific result is theorem 351. You can of course guess why we are calling it E. We want to show that this will turn out to be the E that we want. Okay, an extension of f of degree n which has a root of our polynomial px. But here we immediately run into a problem. Let me actually copy what the author has written. How Herstein has gone through the proof. It's of course because it is appearing in a text. It's not. At this level, it's not entirely formal. It's somewhat like a discussion. It is nice to read such things. So what we normally would do in a very terse and formal mathematical proof, we will not need to write this much. We will just write the bare minimum. Here, however, for example, in this next line, the author writes, this E will be shown to satisfy the conclusions of the theorem. Okay, now about the problem that I was saying we will now run into. First, we want to show that E is an extension of F. However, it is not. Actually, it is not. In the literal sense, it is not. Let's see why that is the case. For for E to be an extension of F, what does it actually mean for E to be an extension of F? It just means that F is a subfield of E. And for that to happen, first of all, F should be a subset of E. But that is not the case, no. F is some field and E is what? E looks like this. Elements in E are what actually? They are cosets of the ideal V, which look like this, fx plus v, where fx varies over our original polynomial ring. We don't see elements of f here. These are ordinary scalars. I should not say scalars because we are not dealing with vector spaces, but these are ordinary field elements These are, however, entirely different objects, different types of objects. These are cosets of an ideal, okay, and these are sets, and these are just some objects. These are of course also elements of this set, but they themselves are sets. These elements, the elements in this field, however, are not sets like that. They may be, but we don't know. So then how can we claim that E is an extension of F? That is by finding an isomorphic copy of F inside this, because while doing algebra, isomorphic structures actually they represent the same underlying thing, okay. There is no essential difference between two isomorphic things. So if you can show that this field E actually has a subfield inside of it, a proper subfield, an actual subfield, but which is isomorphic to F, then it is the same thing in the sense of isomorphism as having F inside this. In that sense, we can say, once we show that F is actually a subfield of this, and hence E is an extension of F. That's what we are now going to do. For that, what we will do, we are now going to define a function. Define the function psi from the polynomial ring fx into our field E by this formula. Fx psi is equal to, we can wrap this off because we have understood what the statement says. We can use this space now. This is defined to be equal to f of x plus v, equal to the coset of v given by the element f of x. Clearly, in fact, we already know that this psi is an isomorphism, because do you see what psi is? It is the, homomorphism, not an isomorphism, I should say. It is the natural homomorphism from this ring into this quotient ring, and its kernel is going to be V. It's that thing, what you have encountered in group theory also. If you have, in place of this ring, if you have a group and a normal subgroup of the group, you can then find this natural homomorphism, group homomorphism from G onto, and that it turns out to be an onto homomorphism, a surjective homomorphism. That same thing, its version in ring theory that we have here. However, let us, just for the sake of doing it once more, show that this is a homomorphism, or at least see how it is a homomorphism. This time, however, keep in mind we are dealing with rings, so we will have to show that psi respects both addition and multiplication. But before that, clearly this is well defined. Okay, for two elements in the domain we have let's do the calculation in the middle. This image is this coset. Don't forget to write this class, okay, because that's how the cosets of this ideal look. Now, by the definition of addition in E, or rather addition in the quotient this here, in this quotient, this thing, this coset is equal to this plus this. This addition that you see is the addition that we have in this field E. And this is nothing but the psi image of f of x, and this is the psi image of g of x. So psi respects addition, and like that this is equal to the corresponding coset of phi. Now, by the definition of multiplication in this field, this coset is equal to this product of two cosets. And that is equal to the psi image of f of x times the psi image of g of x. Keeping in mind our convention of writing arguments to the left of the function in this book. Hence, psi is a homomorphism, is a ring homomorphism. Okay, that we are not mentioning explicitly, it's understood. Now look at this psi. We have shown that it's a ring homomorphism from the polynomial ring fx into the field E. Now we know that f is a subring of fx. This we already know. Because of this, if we restrict psi onto f, that restriction will also automatically be a homomorphism. Do you see why? That is because whatever elements you are taking from fx, on those elements psi behaves like this. psi respects addition and multiplication throughout fx. So in this smaller subset also psi will respect addition and multiplication. From this smaller subset, if you take an element, these are all also polynomials, they are constant polynomials. Okay, so the restriction which also we can call, there is a notation for the restriction but no need to use that, of psi on psi to f, rather I should say, restriction of psi to f is also a ring homomorphism. Okay. The image of f under this homomorphism is clearly equal to this set. We look at what psi does to fx. Now we are going to do that to the elements of f. That's what the images will be. I mean individual images of the elements of f. They will look like this: alpha plus v, where alpha varies over the field, and is a subring of E. We know that when we have a ring homomorphism from one ring into another, then the image of that homomorphism is a subring of the second ring, the target ring. Now, okay, we can now clean this part. Now our aim is to show that this, well, of course now psi is going to be a homomorphism from f into E, but in particular onto f psi, because that is the image. But additionally now we are going to show that this particular extension is one-to-one also, it is injective. So for that, let us take two field elements whose psi images are equal. Alpha psi is equal to beta psi. Then alpha psi means alpha plus v, and beta psi means beta plus v, and this implies this difference belongs to v. Now belonging to v means what? Because v is the principal ideal generated by the polynomial p of x, this means the polynomial p of x divides this constant field element over the polynomial, I mean in the polynomial ring fx, or p of x divides alpha minus beta in fx. Okay. Since not like this. if we suppose alpha to be not equal to beta, then alpha minus beta is a non-zero polynomial, but it's a constant polynomial, and because of its non-zeroness, I mean under our supposition, it will have a degree and its degree is 0. This is a polynomial of degree 0. Since degree of p, degree of p of x is equal to n, which is strictly greater than 0, we would have a contradiction. Okay, why a contradiction though? You see, this divisibility relation implies what? It implies that alpha minus beta is p of x times some polynomial q of x, where q of x belongs to fx. Q of x belonging to fx means divisibility in fx. Okay. Now, non-zeroness of alpha minus beta implies q of x also has to be non-zero. So then you apply the degree formula that we came across in the section on polynomial rings. Degree of alpha minus beta, we are doing all these things under the supposition that alpha minus beta is non-zero. Okay, so that's why its degree exists. By the degree formula, we would then have this. Now, degree of q of x, degree of a polynomial by our definition of degree is always a non-negative integer. So, this is greater than or equal to 0, and that's why this sum is greater than or equal to degree of p of x. But now if this is 0, the degree is 0, the polynomial is non-zero, okay, then this thing would imply this. That is a contradiction. We don't usually write these details. It should be there in the background, on our mind, it should be there. So that's why we directly write we would have a contradiction, and that is why we cannot suppose this. Alpha must be equal to beta. So our supposition is wrong. So let me continue from here. Let us keep this for a moment. So our supposition is wrong. That is, we must have alpha equal to beta, but we chose alpha and beta to be two field elements whose psi images are equal, that is outputs are equal. Now we have shown that the inputs then must also be equal, so psi is 1 to 1, hence the restriction, psi is 1 to 1 means the restriction is 1 to 1, okay, not the original psi, we have left that there itself. The restriction psi from f to, now we are modifying even the restriction, because if I choose to write the image of f under psi here, then that makes sense. Let's just write this restriction itself. The restriction is an isomorphism of f onto f psi, which is this. In the text, this f psi is being denoted like this, f bar. I forgot to do that, but it won't matter because we can write f psi now. So f psi, okay, now note this thing. We have already said that because f psi is the image of a ring homomorphism, so f psi itself is a subring of E. But now that is not just any image. Due to this one-to-one nature of psi, that is now an isomorphic image. F and f psi are ring theoretically identical. So that is why f psi is not just simply a subring of E, but it is in fact a subfield of E, which is isomorphic to the field F. And in fact, because of this isomorphism, the field nature of f psi is coming because of that isomorphism. So this is a subfield of E, that is isomorphic to F. And now we can say yes, E is an extension of F, in this sense that this is an identical copy of F inside E, where this is a subfield of E. In this way, what is the exact language Herstein is using? We can consider E, yes. Consider E to be an extension of F. Now we are going to show next that E is in fact a finite extension of F, and its degree over F is equal to n, the degree of our original polynomial, irreducible polynomial. We now show that E is a finite extension of F with the degree of E over F equal to n. Let us let us also recall what degree really means. When you have a subfield f of E, then we have already seen in the chapter on vector spaces that E then naturally becomes a vector space over F, and this degree is nothing but the dimension of E over F. So now we need to show that this dimension is n. That means we need to show that E has a basis with n number of elements over F, and such a basis now we are going to demonstrate, we are going to produce such a basis. Consider the elements keep in mind the elements in E are what? Are cosets of V in Fx. So we are now going to consider these elements, these cosets of V, 1 plus V, x plus V, x plus V whole square, which turns out to be equal to x square plus V. These are our vectors now, because we are considering E to be a vector space over F. So these cosets are now our vectors, and the elements in F are going to be treated as scalars. So this is equal to x square plus V, like that, till this. N minus 1 plus V. In order to show that these vectors form a basis of E over F, we need to show that they are linearly independent over F and that they span E. Let us show the linear independence of them first. Let alpha naught, alpha 1, etc. these belong to F such that this linear combination alpha naught times 1 plus V plus alpha 1 times x plus V plus, let's just write one more, alpha 2 times x square plus V plus dot 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 alpha n minus 1 to the power n minus 1 plus V is equal to the 0 element in the vector space. Because E is our quotient Fx by V, so the 0 element is V itself. Don't forget that. That is the 0 element in E. This implies then is better, it sounds better. Then we have alpha naught plus alpha 1x plus alpha 2x square, etc. plus alpha n minus 1 x to the power n minus 1 plus V is equal to V, which implies actually you may have a confusion here. The way I have written these things, you may be slightly confused. You see, we have said that E being an extension of F is not a direct literal thing, but rather we are actually considering this degree. No? F, strictly speaking, is not a subfield of E, but rather the image of F under psi is a subfield of E, that is isomorphic to F. So what we are writing here, if you take all the things in in the strict sense, whatever I have written here is meaningless, because what is this product? Does this product make any sense? What I am doing here is that I am multiplying a coset by a scalar. What type of multiplication is that? There is no, we don't have such a multiplication already defined for us in E. However, when you treat E as an extension of a subfield, that multiplication naturally comes from the fact that E is an extension of the subfield. If I simply treat this alpha naught as literally alpha naught, then this multiplication is not there anywhere with us. We don't have a definition for it. However, when you truly understand what this alpha naught is, then it becomes meaningful. This alpha naught is just not simply alpha naught, but it is also a coset, alpha naught plus V. This multiplication makes sense because this is the product of these two cosets, which is already there in E. And according to that, we have alpha naught times 1 plus V, which is alpha naught plus V. But then why are we writing alpha naught in place of alpha naught plus V? That is because of this isomorphism. According to this isomorphism, ring theoretically there is no distinction between F and F psi, and in that association, alpha naught is as good as alpha naught plus V. How alpha naught behaves in F, alpha naught plus V behaves in an exactly similar manner in F psi. Okay, so what we are really doing is this, of course. We in fact are considering E as a vector space over F psi, but we relax this, in the background this consideration is there, but because this field F psi is truly just a copy of F, we are writing things in a somewhat more simple, in a simpler manner. That's what we are doing. This alpha naught is actually not just alpha naught, this is alpha naught plus V. So that is why if you really write this entire linear combination like this, like truly how it is, if you write it like that, you will then see that the operations you have here are all the operations that are already there in E. Just like that, this alpha 1 times x plus V is really this. So when you multiply these two cosets, according to coset multiplication rule, you have this, and when then you add these things, these cosets up, you finally get this. Okay, that's what is going on in the background. Fine. Now this implies what? This implies this polynomial belongs to V, alpha naught plus alpha 1 x plus alpha 2x square and so on plus this belongs to phi, and hence let's continue. P of x divides. Now a situation similar to that alpha beta situation will arise here. Alpha n minus 1 x to the power n minus 1. We don't really know what the alphas are. In fact, it is our aim to show that all the alphas are equal to 0, because then only we will be able to say that these elements in E are linearly independent over F. And by the way, linearly independent over F really means linearly independent over F psi. Okay. Now, if they are not all 0, if these are not all 0, then this polynomial is a non-zero polynomial being non-zero polynomial, it will have a degree, and from the look of this polynomial you can say that the degree is less than or equal to n minus 1. Don't immediately conclude that its degree is equal to n minus 1 because of how it looks. This alpha n minus 1 itself may be 0. The condition that we have written here, that not all of these are 0, does not mean that this is non-zero. That's not necessarily true. Something else may be non-zero. Maybe it's the case that alpha naught is non-zero, but all the other alphas are equal to 0. In that case, this polynomial will have degree 0. So what we can generally say is that the degree is less than or equal to n minus 1. With degree less than or equal to n minus 1. But then px, oh, I haven't written that thing, no? This in fx, in which ring the division is going on, that it's important to write that. But then px cannot possibly divide our polynomial in fx, because px itself has degree n, which is greater than the possible degree of this polynomial, and we have already seen in that alpha beta case why that cannot happen. Hence these are all 0. So our vectors which really are cosets of V are linearly independent over f and really over f psi. Okay, we are not going to repeat that thing again. Next, what we want to show is that these vectors span E. Next, so that means we now have to consider any arbitrary element in E and show that that element is actually a linear combination of these vectors with scalars coming from F. Next, let f of x plus v, so that's how a general element in E looks. This belongs to E. Okay, since P of x is a non-zero polynomial, its degree is there, it has degree, so that means it's non-zero. It's in fact non-constant also, because its degree is at least 1. There exists polynomials qx and rx q of x and r of x belonging to fx such that f of x is equal to p of x times q of x plus r of x. Okay, and what have we done here? We have just simply used the fact that our fx is a Euclidean ring, so we can divide any polynomial by a non-zero polynomial to get a quotient qx and a remainder rx, where I have to continue now, where either r of x is the zero polynomial or it is non-zero, and in that case its degree is strictly less than the degree of the divisor polynomial px, which is n. Now, because p of let me just write the calculation first. Now, our general element fx plus v is this: p of x q of x plus r of x plus v, that by the addition and multiplication, the operations in E is equal to p of x q of x. We don't need to go to the, there is no need to use the multiplication. This much is enough. Addition is enough. This is equal to v plus r of x plus v. This thing is equal to v. Why? Because p of x is itself in v. In fact, v is the principal ideal generated by p of x. So its multiple, this multiple also belongs to v. So this coset is actually equal to v. And this v is the zero element in E. So this sum is equal to Rx plus v. Now either Rx is the zero polynomial or its degree is less than n. Since Rx is equal to 0 or degree of R of x is less than n, we have R of x equal to a polynomial that looks like this: rho n minus 1 x to the power n minus 1 for some scalars in F. I am taking rho, because it's R. You can take anything. Do you see that these two conditions, that R of x is either 0 or its degree is less than n, imply that R of x must be like this? I leave that to you. Okay, it is very easy to see why that is so. R of x must, there is no other choice. R of x must look like this in order for these two things to be true. Hence, our original element now becomes equal to n minus 1 plus v, and that is equal to rho naught times 1 plus v plus rho 1 times x plus v rho n minus 1 times this. And in this calculation again, treat these scalars as those scalars plus v. They are cosets, okay? They are elements in f psi. Otherwise, you will run into confusion again. So, what have we shown here? We have shown here that general vector or general element from E is a linear combination of our chosen vectors with the scalars coming from f psi. So, E is spanned by these vectors. So, E is spanned by our cosets. And hence these cosets form a basis of E over F, or the same thing over F psi. We can then write directly, hence the degree of E over F, or more strictly over F psi, is equal to the dimension by definition, which is n. So we have not only obtained an extension of F, but an extension whose degree is n. Okay, now comes the actual thing. Why are we considering this F? We want to show that this, we are considering this E. We want to show that this E has a root of our original polynomial. Let us now denote the element x psi, which we of course know what it is, the coset x plus v, which turns out to be this basis element, by this simple symbol A. For us now, A will mean this thing. Now comes this next thing. Given f of x belonging to our original polynomial ring, what is f of x psi? It may sound like a stupid question. We of course know what fx psi is. We have defined it to be fx plus v, the corresponding coset, but that is fine, but that is also at the same time equal to something else. We claim that it is in fact f of a. How exactly? Let us see. So to show that, we of course need an expression for fx. Let fx is some polynomial, let that be beta 1 plus beta x and so on, plus beta to the power beta k to the power x times x to the power k. Then first I need ink. It takes some time for the ink to come properly. Then, since psi is a homomorphism we have fx psi equal to this polynomial Now in this polynomial you can actually treat all these things as polynomials, because after all they are. Each scalar is a polynomial and x itself is also a polynomial, and these powers can be considered as powers. You can of course treat x to the power k as a single polynomial, it is, but at the same time you can treat this thing as the kth power of x in the polynomial ring fx using the multiplication that you have in fx. In that sense, because psi is a ring homomorphism, you can apply psi to all these things keeping the structure same. That's what it means for psi to be a homomorphism, right? So what I am saying is that this is equal to beta naught psi plus beta 1 psi times x psi, like that. If we write one more term, it will be this plus beta 2 psi x psi square. First of all, you will apply psi to x square, that becomes equal to this, because psi respects multiplication also. So like that, beta k psi, let me write it here, psi to the power k. Okay, now this becomes what? Truly speaking, beta naught psi is what? Beta naught plus p plus, like that, beta 1 plus p. But this x psi is what we have decided to denote it by a. So this is a plus, yeah, it has been good to write another term, things will become much more clear. A square plus beta k plus phi a to the power k. But then again, recall that for us, because our f and f psi are isomorphic fields, so these cosets are the same thing as their images under this isomorphism. That is, this beta naught plus v is the same as beta. It's that thing that we were discussing back there. So we finally get this. When people first encounter this type of things, it looks confusing and seems like it's wrong, but it's actually not wrong. Isomorphic systems are the same, only their elements have been given different names, that's all. They look different, okay, but the underlying structure is identical. It's like looking at something in visible light and then looking at it in infrared or ultraviolet. It will look different, but the thing stays the same. And this is what? This is just the evaluation of f at a. So what we were saying back there, that has now been shown to be true. In particular, So whatever we have just now said for a general polynomial fx, we can also say for our px, since p of x belongs to fx, we have p of x psi also equal to p of a. However, also by the very definition of psi, p of x psi is equal to p of x plus v. So that means what? Oh, what have we written here? P of x psi belongs to p of x plus v. Okay. Now I have messed up a little bit the writing here. However, also since the p of x is not just any polynomial, p of x belongs to v. So if we apply psi on p of x, whose kernel is v is the kernel of psi, we get the zero element in E, or in more detail we get this. This is equal to 0, I am writing, okay. In our E, this v is the zero element. Hence, p of a is equal to 0. Do you understand exactly how this is 0? What we have shown ultimately is that in the expression for the polynomial px, in place of x, if you put this thing, then you get the zero element in v. This of course is an element in v. So whatever you are going to get after substituting the indeterminate x in the polynomial p with this particular element in E, whatever you are going to get, that is going to be an element again in E, but that element now turns out to be 0. So what does that mean? It just simply means that this x psi, or which we are denoting by a, that is a root of the polynomial p in E, because this x psi is actually in E. So that's how we have obtained an extension of the desired type. It is an extension of f, its degree over f is n, and it has a root of our polynomial. The field E has thus been shown to have all the desired or required, same thing, properties that we were seeking in the theorem. So the theorem is, let's just end it here itself. So that's how every polynomial has a root in an extension field, every irreducible polynomial. Now we are going to go to the case of a general polynomial. If fx belongs to f of x, then there is a finite extension E of f in which fx has a root. Moreover, the degree of this extension is now not exactly equal to the degree of our polynomial, but less than or equal to the degree of our polynomial f of x. I hope it's visible. This is degree of f of x. The statement of this corollary as it stands is a little incomplete. There is one detail missing from here, which is why I don't like these things about Herstein. He misses some details, and those details are actually necessary. Without them, technically strictly speaking, the corollary is false. And that detail is, you can clearly see, we need to say also additionally that the degree of this fx is greater than or equal to 1, like what we had in the theorem. Now you can argue that because it's the corollary to the theorem, so it's understood that the degree is greater than or equal to 1, but no, that's not how mathematics works. You have to have a level of formality, otherwise confusion will reign. So we are going to, of course, assume that the degree of f of x is greater than or equal to 1. And because the degree of f of x is a non-constant polynomial and hence a non-zero polynomial, and because it is non-constant, it is a non-unit polynomial. That is why, by the fact that fx is a Euclidean ring and hence a unique factorization domain, fx has an irreducible factor. Just like, what I am trying to say here is this: if you have an integer, an ordinary integer, say 2 or 12, if your integer is greater than 1, then by the fundamental theorem of arithmetic you say that it has a prime factor. 12, for example, has 2 prime factors, 2 and 3. 2 has only 1 prime factor, 2. But you need to make sure that your number is greater than 1, or at least it is neither equal to 1 nor minus 1 if you take negatives also. Just like that, in this Euclidean ring, the integers also form a Euclidean ring. This polynomial ring is also a Euclidean ring. That thing, that unique factorization theorem, comes into effect only when the polynomial you have taken is not a unit and also not 0. Then it will have an irreducible or prime factor, and that will be ensured by it having its degree greater than or equal to 1. So we are going to write, under the assumption that its degree is greater than or equal to 1, let p of x be an irreducible factor. That means an irreducible polynomial that divides fx in fx. Oh, irreducible factor of what? of our original polynomial. And this looks quite bad. Irreducible factor of fx in f of x. Any root of p of x would also be a root of f of x, naturally, because p of x is dividing f of x. Now, by the above theorem, there exists an extension E of f that has a root of p of x, and the degree of this is equal to the degree of p of x. But because p of x divides f of x, the degree of p of x is less than or equal to the degree of f of x. So that completes the proof of this corollary. So now we know that not just irreducible polynomials, in fact any polynomial has a root, maybe not in that field but in an extension field. And in fact this is how you have the field of complex numbers from the field of real numbers in an attempt to find a root of this polynomial. When complex numbers are introduced to us for the first time, in fact this is how they are introduced. We are, although at that time we are not told about polynomials themselves but about an equation. Same thing, we are told that this equation has no real root. That is the same thing as saying that the polynomial x square plus 1 in Rx has no root in R. You cannot replace x with a real number and get 0. So that is why we need an extension, and this particular polynomial is irreducible over R simply because of that fact that it has no root in R. And so what one does is this: one considers this quotient ring. X square plus 1 is irreducible over R, so this principal ideal generated by x square plus 1 is a is a maximal ideal in this polynomial ring. So this quotient is a field, and this field is nothing but your, you can say it's isomorphic to the field of complex numbers. Okay, so that's how you get the complex field. And in fact, if you go through this proof, in this specific case, you will see exactly which element here corresponds to that imaginary unit I in C. They are the same thing, they are isomorphic, so you can make sense of those things. In the next field, we are stopping the video here itself. In the next field theory video, we will see that not just one root, we can in fact have an extension, in fact a finite extension, which has all the roots of a given polynomial. We have already proved in the previous field theory video that a polynomial of degree n can have at most n roots. So we can in fact find an extension where all those roots are there. And once we have that, we can then find an extension with the smallest possible degree. That extension will be, of course, a field containing our original field. It is, I think, called splitting field of the polynomial, and we will see many things related to that notion. Okay, so that will be all today in this video. And coming, today is Tuesday, no? So coming Friday we again have vector spaces. So that's just it. If you want to say something on these things, you can write in the comment section below, and see you on Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.